settings. And that's what's happening right here. In this setting of the Brouncker continued fractions, you see pi, and now the Leibniz gate constant is showing its value. So now, with the even numbers, 2, 4, 6, 8, and so on, same kind of continued fraction, the 2 gives you L squared over pi. And then the next one gives you its reciprocal, pi over L squared. L squared over pi, and so on. So that's how they appear. Okay. And you can make morphings out of those and so on. I just want to take one last minute to show you what Wallis says about how Brouncker teased out all these continued fractions. Okay. And this is also what Euler picks up on, the same thing. He says, look at this. His infinite product from 2 over pi. And then he says double every number here. Double every number. Okay. Now, then multiply by 2, and what you'll get is this. 2 squared, 4 squared, 6 squared, 8 squared, 10 squared. Okay. Now, this is just amazing when you look at it. He says, okay, now the trick is to find numbers A, B, C, D, E, F, G that have the following property. A times B will be the 2 squared. And B times C will be the 4 squared, and so on. Okay. And if you do that, and you do it right, you pick the right A, then what happens is the B's cancel, the C's cancel, the D's cancel, you're just left with A. Okay. Now, what does it mean to pick the right A? Now, take a minute and think about this. If you say AB equals 4, once you pick a number for A, you can calculate B. B is 9. Now that you know B, you can calculate C. And now that you know C, you can calculate D. So once you know A, you know everything else. Okay? So you can start with anything for A, and then you get B, C. However, as Euler puts it, there's only one A that satisfies the principle of uniformity, whatever that means. He never explains what it means. That satisfies the principle of uniformity, and that's the one that gives you the 4 over pi. Okay. And if you study that, what it apparently means is this. If you look at the sequence, A, B, C, D, D, like that, okay? And you imagine it going on to infinity, and you study it as a sequence, well, of course, the numbers are getting bigger all the time because they equal these squares. Okay, well then divide A by 2, divide B by 4, divide C by 6, and so on. And look at that sequence. Okay? And that sequence, now, does that approach a limit? Turns out that it doesn't unless you pick the right value for A. Only the value 4 over pi gives you a limit. Any other value you pick, the thing oscillates between 2 values, and there is no limit. But the only thing that will zero in on one limit is this special value 4 over pi. It's a mystery to me. I don't fully understand it. Euler never quite explains it. Whatever Brouncker and Wallis were up to here, we only have a partial. We have things like this. There's a picture like this in Wallis. Okay. And a couple papers have been written attempting to conjecture just what Brouncker was up to when he got the continued fraction. Almost nothing had been done with continued fractions at that time. Continued fractions were essentially almost unheard of at that time. None of them really looked too good to me anyway, partly because all the people who wrote those papers recently, none of them recognized that there was more than one continued fraction. There aren't really many continued fractions, and they just stare at the one. Well, if you just stare at the one, then you get no idea what's going on here. Euler has his own conjecture as to what happened. Euler says that Brouncker got the first series, not from this, but from the Gregory-Leibniz series. You know the Gregory-Leibniz series? I'm sure you know it. You just maybe the name pi over 4 equals 1 minus a third plus a fifth minus a seventh, and so on. This series was known, but whether or not it was known to these guys, okay, I mean, information didn't get out real fast in those days. It doesn't spread around. But if you start with this, you can very easily get the first of Brounker's continued fractions. That was an exercise I set for myself many years ago, and I actually did it. Okay, it isn't that hard. And Euler shows it in his paper, brilliantly, of course, how you can go from this to the continued fraction. Then once you've got the first one, you can conjecture the others from this. You can guess at them, and then try them out, multiply them together to see if they're working, and you can see they are. If you try multiplying them, they actually work. You can see it taking place. So that was Euler's conjecture as to how it happened. Okay. I asked Steedall if she agreed with that. She was the woman who translated this thing and also wrote a paper on it, and she said she didn't like what I wrote. But anyway. So I think I've just reached the end of my time.
Thanks a lot.
So thank you very much.
Thank you for beautiful experimental and
Thank you.
historical talk. That's perfect for the seminar. I forgot to say, Tom will be glad to answer questions in private. Also, I forgot to mention, we'll be taking Tom out for dinner at 6:45 at the Evelyn restaurant on Eastern Avenue. And you're welcome to come. But if you'd like to come, please let me know right now. Thank you.